We now know something about the electronic transitions in polyatomic molecules and something about the vibrational states and rotational states that are also within polyatomic molecules. In this video, I would like to present some sort of qualitative summary about the sorts of things that can happen when one performs an electronic excitation spectroscopically on a molecule. Now, to do this, I'm going to employ something called a Jablonski diagram, and you'll see what this looks like in just a moment. But I want to write it out here so that you can look it up if you wish. All right, and in this, what we're going to do is we're going to neglect drawing pictures of potential surfaces because for polyatomics it really is kind of difficult to represent all the various vibrational degrees of freedom in that. So instead we're going to be very, very abstract. And we're going to start by describing our system down here in state S0, which stands for the ground state that is a singlet. A lot of closed shell molecules start in a singlet state down here. Now we're going to suppose that there's a few other electronic states, and I'm going to judiciously place them in various locations. So for example, this one will be the first excited singlet state, which I'll call S1. And maybe we'll have another state up here, which we'll call the second excited singlet state. So that's S2. Now, many molecules also have states that do not have the same spin multiplicity. So for example, we may have a triplet state, which I'll draw over here and call that T1. Now, one of the things that I guess we should be aware of is that the same selection rules for spin that we found for diatomics are also generally going to be true for polyatomics. That is to say, we're generally going to have that delta S is equal to 0, which means that if we have a singlet ground state, which most of the closed shell molecules we deal with are, then we'll also have transitions only to singlet states. If we, for example, have a triplet state as our ground state, then we would have transitions to triplet states. Now that doesn't mean that triplet states get left out entirely in the cold, and we'll see how they get involved in the post-excitation dynamics in just a moment. All right, now with each of these states, what I'd like to do is suggest that these represent a manifold of states. And by a manifold, I mean on each electronic state, you think of them as representing an electronic potential energy surface, there will be a series of vibrational lines. And so I'm just going to represent them abstractly like this. Okay, not necessarily trying to imply anything about relative frequencies or anything like that, just that all of these electronic states will have a series of vibrational states. Now I'm not going to draw them all, but you should also realize that each of the vibrational states has a series of rotational levels, and those are a little more closely spaced than the vibrational states. Okay, and this is going to be true on all of these surfaces, so this will have rotational states and so forth. All right, but we're going to focus just on the sorts of dynamics that can accrue when we begin to excite this molecule with a beam of light. All right, so the first step is that we could have an excitation that brings us from our ground singlet state up to our excited singlet state. All right, so this one photon transition is something that we could write as S0 going to S1, a direct excitation. Now, we can also have excitations that take us directly up to the second excited singlet state. So this would be S2 being excited from S0. Okay, both of these are excitation steps. And so I want to say a little bit about each of these. So absorption of a photon, in this case, is an excitation step. Okay, that takes us to a higher energy surface or a higher electronic state. Now, one of the things that we're going to care about is how fast does this happen? And typically, this excitation happens very fast. It happens on the order of 10 to the minus 15 seconds. Okay, and if you're keen on Greek prefixes, that represents a femtosecond. So it's a very, very fast process. All right, now once it has gone up here the molecule can do all kinds of things. Now, remember that these molecules are typically not in isolation. If they're in outer space, they're in isolation. If they're in a molecular beam, they're in isolation. But they're undergoing collisions, they're undergoing interactions with other molecules, and so a lot can happen. In particular, one of the things that can happen is that we can see some trickling down of this excitation. And that's something that I'll call a vibrational relaxation, or I'll just call it relaxation process. And this relaxation has lots of different names, and so as you encounter this in the chemical literature, you might see it represented as an internal conversion. Okay, this is also used to talk about moving from one singlet state to another. So maybe I shouldn't probably put that one here, but for example, we would have a vibrational redistribution, or vibrational relaxation is another way of putting this. And whatever we call it, this is something that typically happens on a much slower time scale than the excitation does. It typically happens on a time scale of roughly 10 to the minus 12, or that is 1 picosecond. Could be as long as 100 of those picoseconds or so. But it's taking place, I should say not 100, it's 10 to the minus 14 seconds that this is taking place. But it's taking place on a slower time scale than the excitation itself, about 10 times slower. All right, now when we have all this going on, we can have also what amounts to a crossing from one singlet state to another. So I'll just draw that as a wavy line that connects from here over to here. So if we had excited the second excited singlet state, it can still cross over here, not losing energy or anything. And this is what we would refer to as an internal conversion. So maybe it's better for me to reserve that term here. And this internal conversion is, for example, what's happening when I go from S2 to S1 up here. As a means of redistributing the energy by changing the electronic state that the molecule is in. All right, once it's come over here, it would also undergo this same sort of vibrational de-excitation or relaxation that we see going on here. Now, another type of dynamic that can go on is, I should mention how long this takes. Okay, the internal conversion, this is what is something that is 10 to the minus 14 to 10 to the minus 11 seconds. So a little bit slower. All right, while it's relaxing within these excited singlet states, it's undergoing collisions and other things are happening, and it's not out of the question that it could undergo a crossing over here to the triplet state. All right, this is a process called intersystem crossing. And basically an intersystem crossing is when you are going from one state to another state and they have different spin multiplicities. So I'll write that as between states with different spin. So singlet to triplet in this case. Sometimes it's abbreviated ISC, intersystem crossing, but then you end up over here on this triplet state where once again we can have a relaxation that trickles down here from this higher vibrational state down to a lower state, a radiationalist deactivation, if you will. And this can also subsequently go internal conversion to another triplet state and so forth. So there's lots of things that can happen here. All right, now finally, I'd like to describe what can happen, because ultimately we're going to come back to the ground state. The ground state is the one place that is the most stable out of all of these possibilities. Now, in order to represent this, I'm going to start basically just with S1 over here, T1 over here, and S0, our ground state. All right, at some point we've relaxed down to something approximating the vibrational ground states of these electronic excited states. And what we'll see actually is an emission of light back down to the ground state. In the case of going from a singlet state to a singlet state, this emission of light is called fluorescence. Okay, so fluorescence is emission to a state with the same spin. Now, fluorescence takes place on a somewhat longer time scale, and we're talking now about nanoseconds, or even close to a microsecond, tenth of a microsecond. So this is much longer. Now, remember that exciting the molecule happened in 10 to the minus 15 seconds. So 1,000,000 times that interval is how long it takes the molecule to get around to fluorescing. Now, 10 to the minus 9 seconds is still pretty quick, but we have to think in terms of how the molecule feels. And in this case, this is a pretty slow process. But it's not as slow as the process that the triplet state undergoes. It also can undergo an emission, and in this case, the emission is called phosphorescence. Okay, so phosphorescence is essentially emission between states of different multiplicity. So emission to a state with different spin. And I guess I should probably add the word multiplicity to be sure I'm communicating correctly. And phosphorescence now takes place on a really slow time scale. In this case, what I mean is something like 10 to the minus 3 all the way up to 10 to the 2 seconds. So in other words, minutes can take for phosphorescence to occur. And if you've ever played around with phosphorescent material, this is probably not a surprise for you. All right, so these are all various things that can happen after we have excited a molecule. There is a lot of action going on in these molecules and a lot of things that they can do on these excited states. They will ultimately end up back on the ground state through fluorescence or phosphorescence. They can also end up on the ground state if, for example, the ground state, say comes up and the excited singlet state comes down and they have an an internal conversion at a crossing point between the two surfaces. Now there's there's a couple of other outcomes that can happen from excitation, but one other that I want you to be aware of. I'm not going to say much about it, but we can also have photochemistry. Whenever we excite a molecule, we're putting lots of energy into the molecule, and these excited state surfaces cause the molecule to move in different ways. It's basically causing the molecule to begin vibration. A famous case of this is the case of rhodopsin. Retinal is a long linear chain polyene that's attached to the rhodopsin, which rhodopsin is a big protein here. And what tends to happen is that when this thing it starts off bent, it actually starts off looking like this. And what happens is when it absorbs some light, it straightens out. It becomes like this, and then it breaks off. So in other words, the absorption of light in the case of retinal is the trigger that begins a series of chemical reactions, but it starts with a photochemically induced reaction that then triggers other chemical reactions that ultimately turns into a nerve signal that tells your brain you just absorbed a photon. All right, enough for this one. I hope this has made some sense and that you have now a good general view of what's going on when we have fluorescence excitation processes going in polyatomic molecules.